So good evening, everyone. I welcome to you all in the today's workshop on brick design and analysis concept. So we have today's speaker, Mrs. Geeta Prakash. She having 20 plus year of experience in the field of structured design, the building information modeling, the project management. And she having the expertise of more than 25 software related to project management, designing, modeling, and analysis. She also worked with many MNCs like L&T, Chennai Metro, and many big civil industries. Welcome to ma'am in this today's session. And I would like to tell you about the session attendance point. Here there will be a two steps attendance. First, you have to mark in the middle of the session in the comment box with your name. And second, at the end of the session, we'll be providing you with Google form. You have to write your name that you want to reflect on certificate. So please make sure whatever name you are going to write, okay, it will be the same thing reflecting on your certificate. You can also subscribe to our channel and we'll pick some random student for providing some like innovative courses from our side. And all the students will be getting the certificate of this today's workshop and will be guiding you how to download your certificate by tomorrow's session. So thank you so much. Ma'am, you may start the session.
Yeah, I can start. Hello. Okay. Hey everyone. So today we are going to have a session on the bridge design concepts, the loads, and the different type of bridges. According to the classification, how many bridges are there? So that will be a 1 hour session. So let's begin. We have a bridge design. What is bridge design? An engineering process and an art. So we are going to see the modeling and analysis of bridges also. And we are going to see how the concept is developed and how the components are selected. So a lot of selection criteria are involved. So we are going to see all that things. Structural engineering, as you know, is the art of designing and making economy, elegance, all type of structures, that is buildings, bridges, frameworks, so that they can safely resist the forces to which they may be subjected to. And what is design? It is a process of determining the location, material, size, and the type of structural elements which should be resisting the forces which are going to act on a structure. That is the design process. So let's see here, you see in the picture there are different type of structures available. It is not, we might be in a interpretation that bridges are only one type. We saw suspension bridges or other kind of bridges, but here you can see that there are a lot of bridges. They're called viaducts, river bridges. You can see the underpass, drainage boxes, underpass, overpass. So there are a lot of structures when you talk about the bridges. So why do you need the need to build bridges? So it is a bridging kind of a thing between two pathways, or it's an obstacle over a roadway or a pathway or an obstacle. That is the definition of a bridge. Okay? So the purpose, so that traffic can continue without uninterrupted uninterrupted in the alignment. Okay? Purpose to become serviceable and safe during its lifetime. So that is the bridge purpose, design purpose. So why sometimes the bridges fail. So what can go wrong? So the process where the bridges fail, where it can go wrong is during the planning and design. Some bridges fail during construction, during normal operational conditions, during abnormal like heavy winds, etc. over a long time, maybe due to non-maintenance and during decommissioning. So the structural design of the bridge should be reasonably such a way so that the structural designer considers all the factors to prevent such thing that happens that will hamper the bridge purpose. What are the designs to be considered? Okay, when you design a bridge during the lifetime of the structure, to design to resist all load combinations, there is a code which you have to refer, where all load combinations should be taken into account. Equilibrium and strain, that also should be maintained, and temperature change, pre-stressing movements, supports, all these things should be investigated properly to have a proper design. According to the type of bridges, we have lots of classification, according to which there are a lot of bridges. First is the utilization and purpose. So based on purpose, there are a lot of bridges. Then topography and location, where your bridge is going to be situated, overall geometry, and the structural system and framing. We all will see all the points. Fabrication and construction method, and structural material, whether steel bridge or concrete bridge is required for that area. So that should be all taken into account. So the different types. So you can see that the classification of bridges, when you say about the utilization, it can be a canal, it can be a aqueduct, a highway, a railway, pipeline also. Fabrication and construction purpose, we have cantilever construction, incrementally launched, in situ concrete bridges, precast. So topography is flyovers, it's also a bridge. You see different types of flyovers, so you will see all kind of international bridges. Then elevated corridors, metro station kind of a bridge, valley bridge, river, and then straight, curved or skewed bridges based on the geometry. And based on the structural systems, like beams, you have simply supported continuous bridge. When you talk about a frame bridge, we have V bridges, cable stayed bridges, suspension bridges, then arc bridge. We have poly arc, a lot of different types of arcs, fixed arc, hinged arc, tied arc. We are going to see an arc bridge, how to design it in our software later in the later session. Then we have structural materials, stone bridge, RC bridge, pre-stressed concrete bridge, pre-tension and post-tension, then steel, wood girder, steel girders with RC deck. All these are different kind of bridges. So here we have some of the types of bridges in a pictorial representation. You can see the beam, simple and frame bridge, independent arc bridge when you talk about the arc bridges, side arcs, then suspension and cable stayed. So this is a suspension bridge. This is a cable stayed bridge. The difference between the suspension and the cable stayed bridge, you're able to see it in a pictorial representation. There is a cantilever bridge, balanced cantilever. Here you have the abutment where it is only cantilever. So that's called a cantilever bridge and a K-frame bridge. Both sides. Here it's an abutment, here it's an abutment there, and then it is supported by a K type of a frame. So here a steel bridge is available. You can see that There are the components I'll explain while moving on. This is a steel bridge. We say truss bridges. Okay, so the name of the bridge is shown here. Here, this is of RCC, this is of steel, this is again of steel. Okay, so this is a truss bridge. Truss bridge. Here we have one more truss bridge with a different shape. So this is made of concrete. This is of steel. This is called a deck, composite deck. And here you have the abutments and the piers available. Again, one more steel type of bridge. Then arch is there, then there's a truss is there. So all these things are made of plates, steel, angles, castellated beams, steel beams. These are called castellated beams. And this is also a truss bridge. This is called a Rama bridge. Here all is made up of steel, the top portion. Call it a superstructure. And here we have a concrete bridge. These are called the columns and these are called girders. You can see the shape. Different kind of shapes of beams are available. So very difficult in construction. You can see this is a Taxon bridge. Here the shape of the column, it's a V-shaped bridge. The column itself is V-shaped. Okay. And here it's called a monolithic. You can see the difference here. The monolithic is the foundation is constructed along with that, and there is no separation of this structure and the substructure. Okay, so this is called the superstructure. This is called the deck. There's a railing here. This is a beam or the girder which is passing through. Here, one more type of an arch opening. You can see how the shape is going and bending in that way. So this is a big pier. We call it a pier, and at the corner they are called abutments. And you can see how much length of this column is. Here is. So this is also a monolithic kind of a bridge. This is one more type of bridge. This is again a concrete bridge. Here we have one more concrete here, somewhat monolithic. You can see the shape. Both are at the same point. You can see that here there's a truss bridge, a steel bridge, as well as concrete bridge. As I told you, based on the location, based on the purpose, topography, everything is has to be considered. Which type of material we're going to use. So this is also monolithic. You can see the difference. It is constructed from the beam, from the foundation, and then it's going on. Here there is no separation. Here we have the components of the bridge. There is a railing. There is a roadway beyond that. This is one of the cable-stayed bridges. They're called these are called pylons. The center portion is called pylon, and they are connected through cables for tension with a very high tension cables. They're connected. You can see the shape of the road, how it's going to. It's not straight. You can see it's a very curved one and complex structure. So there are 15 bridges over this river. So one I'm doing that done it closely so that the bridge has a main span of 300 meters. 300 meters, which is 980 foot, and one of the largest cable-stayed bridges. You see, these are high tension cables. They are connected with an incline support to this pylon. And this whole tension cables are going to support this deck. This is one more, the first cable-stayed bridge, and the second longest span. This is one more cable-stayed. And there are expressways. The expressway is a very complex bridge, you can see how it's not straight. So many expressways are going above and below and they're turning. So this was opened to service in 1981, which is a total distance of 207 kilometers. So claimed to be the longest bridge in the world. This width is 27 meters. This width, you can see, these are the lanes. 2 lanes are there. So this is called 2-lane bridge. And the section is a box girder. Section is called a box girder. We will see that sections. These are called sky train bridges. They are like expressways only, or you can say highways, but they're it is not straight. It's so complex. It is. There's one more expressway or highway bridge, maybe for a monorail, or you can walk through also. This is again one more complex type of a bridge. Now we have the bridge components. So what are the bridge components that we saw in the previous slides? There was a deck. So the deck is combination of slabs, girders, and diaphragms. Then there was a substructure where you have different types of supports. Piers were there, pylons were there, arches with the cables. We saw the post-tension cables in the cable stayed bridges. Then there's a foundation and support. Foundation, you can have pipe caps, isolators, which we are going to see. Then abutments we are going to see. Footings, we are going to caissons we are going to see. Then connections. Now this and this substructure and the superstructure. Superstructure and the substructure and the foundation. They have to be having a connection. If it is not monolithic, by means of bearings, joints, and other restraints. Then there is barriers. You saw there was the railings, barriers, then the drainage for water to flow, rainwater to come down. That has to be done. And lighting is there. So all these things comprise of the bridge component. Now, different type of structural elements. We saw the foundation. In that, we have the surface, deep, and friction type. A lot of foundations can be this surface foundation means spread, combined, etc. Deep means bearing, pile foundation, caisson, shafts, all these things. Caisson is a well type foundation. Then again, there are floating. Some of the foundations, if possible, at this time, you will see. And superstructure, you will have the cross section of the beam, where you have different type of cross section. Box is there, trapezoidal with opening. So here you have the deck systems available for the different type of bridge that we saw. For Rama 6, then there was Rama 7, 5. Then Taxon we saw. Okay. Turf we saw. So the shape of the girder or the deck which we saw in the real-time photo, it was like this. So we could not see the section wise. It was only a imagine 3D isometric view. Here we could see how the section of the girder and the deck will be. Just like a trapezoidal shape or a pentagon, a hexagon shape. Here it is a box girders. These are box girders with holes inside. So there are a lot of sections available. Okay. Here this is again a hexagonal type. There was a steel. This is a steel truss bridge. Here you can see the difference between here the bearing is placed here. Here it is monolithic. Okay, so different type of girders and beams under the deck. Here you can see this is a box type, which there you can see that they are small sections. They are brought and placed in such a way, and they are connected. So they are called box sections. If you cut and see, there will be box. This is one more type. This is a rectangular type. Under the girders, you can see the shape of the girders here. So this is a different shape of a column. These are rectangular girders. These are steel bridges. This is a one type of a girder. This is an eye section. You can see the eye here. These are rectangular concrete bridges. And here you can see that this is monolithic, but here there is a separation. This is monolithic. You can see from the underside how it looks. Here again, you can see there is a isolator here. Some kind of a bearing will be available. We'll see that different. So here the section which you saw, you can see that's a girder section and the traps are shaped. Here is a different shape. The small bearings will be placed here. I'll show you the different types of bearings and why they are placed. So this is a steel bridge on underside of the bridge, and you can see that these are called the plates, gusset plates, and they are bolted. So one more type of a bridge that you see here underside the section. The basic objective of this to show you how the section of the beams look. So these are the different types of sections we saw. Some of the sections, not all. There was a box girder, there was a precast girder, and then there will be a top of the concrete, these type of girders. Steel beams were there, and over that the deck was placed. Here some flat slab were there. Here there was a solid type of a beam. Over that the deck was placed. These rectangular tie beams are placed. You just saw it in the previous slides, all these things. So I am just showing you the section, how it. So there are different type of supporting components. If you see, there's a steel beam. We saw that over that there was a concrete deck was placed. This is so there's again a precast. Then precast panels will be brought and placed. Then you have open steel and precast boxes. Open steel and precast box, this is closed one. And there's a monolithic made of concrete. Again, there are different type of deck cross sections. So here you can see the rectangular, this is monolithic. So this is an integral concrete box section placed. Here these are called the shear keys. Shear keys. Okay, void type. These are the void type where you will have a hole inside, void inside. Then there is again these kind of integral concrete. The shapes differ. You saw these kind of shapes of columns, different type of shapes of columns, which are precast. Built somewhere, constructed somewhere, brought to site, and then they are fixed. Then they are called pylons, piers, and pier frames. We saw different types of pylons. So they are the single pier made of concrete hollow sections. So different type of pylons are available. Hollow steel section piers. So we saw mostly hollow sections and solid concrete sections. These kind of pylons, these are called pylons. And these are, you can see that high tension. Here the support, they're inclined and they are pulled. The jack with some kind of a tension, that amount of tension, some value, and then they pull it, give that strength, and then they fix it. This is one type of another type. You can see that here they are fixed. These are called incline supports. They are pulled, all the cables are pulled and they are fixed here. You can see this was the shape, one of the shapes that we saw. V-shaped columns here. You see all kind of shapes are there. These shapes have a purpose. So without a purpose and the objective, the shapes are not formed. The piers can be of varied height also. There are short and long, very long span. The height is so large. Some where the height is very small. So based on again the
Hello everyone. There is some disturbance due to wet weather condition. I will be joining within a minute only. So stay connected here.
so we have different piers that you saw. Here also there is different type of
Hello everyone. Okay, so now you may mark your attendance also. From here we are going to count your attendance. Thank you so much.
okay. So we were seeing the different types of piers available. The long span piers. The height is, you see how much, say around 10 meters in that way, the height will differ. Okay? So this is one more different kind of a shape of a pier. Here you can see again there is a isolator. That means this deck is connected to the superstructure through an isolator. Okay. So now we will see the purpose of this isolator a bit later. So here also one more shape, but this is monolithic shape of a pier. Here one more monolithic. So different types of piers and pier cap is available. There are box sections. Okay, monolithic sections. See here you can see the difference. There is a small connector. This is called a bearing. So I'll tell you when I come to the slide what is the importance of this bearing. Okay, so this is connected with the substructure by means of some connector. These are called isolators. So again, type of sections of columns that you saw, I showed you so many pictures in that you could see this is the plan view, this is the cross-sectional view, side view, elevational view of the different types of piers available. Here from the top view, you can see how the shapes vary from the plan as well as the elevation. So these kind of can be modeled, sections can be modeled in different tools for different type of analysis. You can see how there are two tier highways. So one for rail and maybe the roadway. So you can see how complex this is. Again, a monolithic nearby image of that. Here there's a gap. So this is the deck and that is sitting over the pier. Here there will be a bearing. I'll tell you the purpose of the bearing. Okay? So again, one more type. These are the different types. Okay. So however complex may be, this is a V-shaped column which we saw in the section. This is again one more type of a V-shaped, a C bridge. So then we go for the abutments. Now, what are abutments? And the different types of abutments: open type, closed abutments, cantilever. So these are called the abutments. When you have in the middle the piers, they are called piers, and when you have on the bank, they are called the abutments. This is called an abutment, and here you call it as a pier. So this is an abutment. When the column, when the pier is near the bank, you have a wing. For that, there's a land. So that is called the abutment. This, the central one, is called the pier. And under that, you'll have the pile cap. Then under pile cap, you'll have lot of piles driven inside. So based on the soil at the foundation level, they will decide whether it should be spread footing or whether it should be a pile foundation. So loose soil, all kind of things. So that is separate scope where the foundation itself is separate. The components we saw of the bridge was bridge deck. This is the guardrail and this is the approach slab. There is a wing wall. So we'll see some of that in this picture. So this is the wing wall. This you can see here is the wing wall, and this is a steel truss bridge. This is again an abutment. This is a wing wall of it. So here you see it is the nearby of that land or the shore or the bank. You call it as an abutment. And you can see how the rods or steel reinforcement is then over that it is casted. So these are called cast in situ bridges. Here there is a abutment, but you can see that it has worn out. So this is a abutment, but it has worn out. They are not permanent. So because of the soil erosion, they got worn out, and you can see the section how it looks. It's a steel one. Now we go for the bridge bearings and the joints. So what is the purpose of giving the bearings? Bearings connect the superstructure and the substructure. Why? It allows for movements, yet it transfers the forces. Okay, now there are different types of materials in which the bearings are made. So they are made from rubber and steel plates. They are made from steel. Then steel arm with large movement, they are called rocker. They are pinned or hinged, a roller. Then the rubber and steel plates are also there for cushioning effects. So different type of again bearings are available. So these are the bearings. Sliding bearing. You can see the spherical bearing. This is called a rocker bearing. You know, what do they do? What is the purpose? Why do they connect the superstructure and the substructure? You know that the bridges are very crucial structures. So once what happens, the bridge, the vehicle moves, and at a time when earthquake or some kind of a seismic effect comes, or a wind effect comes, if the deck structure gets very, they should. So in such kind of cases, now what happens is
So hello everyone. I think there was some power issue. So you were learning about the concept of types of bridge, different elements of the bridge. Because whenever you are going to design the bridge, the elements, the different structure element matters because there will be different load condition on different parts, right? And you have to understand how all the loads are flowing from superstructure to substructure. That's the only role of engineer. You have to create a system in such a manner load should not concentrate on a single point. Should always move from superstructure to foundation level. That's called the substructure part. So today is like you will be learning all these elements part, the force flow, different elements, what the function of each and every elements using in different types of bridge. And tomorrow we'll be doing the practical analysis using OSTO coding or maybe or like according to I said coding. So OSTO coding we are using for the Americans like American Association of State Highway. So that of company they are using like such a codings to generate the combinations of different loads. So this is the like a major part you have to concentrate because you will be getting wonderful learning through here.
So we saw that there are different kind of connectors available and the bearings and the control devices are available. You can see one more type of bearing, a slider bearing. There are rollers inside. There a slider bearing is there. You can see that this type of bearings are for heavy kind of bridges. So that will vary based on the purpose, based on the size of the bridge. The bearings can be varied. Very high type of bearings. You can see that now it is nearer. You can see that this kind of bearing is placed between this is a superstructure and this is a substructure here. One more. Okay, so they will differ. This is one more type of a bearing. One more type of a bearing. Here also they are placed. Slider bearings, rocker bearings. So you can see that this will help in the movement of the deck and make it flexible so that less damage is there when some forces are heavy. Whether it can be wind also. Now here you see that this is a type of an expansion joint given in the bridge because due to temperature there is a expansion. So due to that the concrete expands and contracts. So in order to have that kind of an effect so that the span does not have a change, they give these expansion joints. Here you can see that different type of one more type of a bearing is available, which is a device which connects the substructure and the superstructure. Here you see the bearings. These are restrainers and the bearings. They are tied down. Again, there are different types. So based on the purpose, based on the cost, everything is considered while selecting. Here bearings with larger movement. This is again for this is the earthquake forces. These are specific. That's why it's a bearing with large movement. So these, that's why I told you when these try to slide or move, the forces from the substructure and superstructure is lessened by this bearing, these kind of bearings. How do we choose the right system and the component? A lot of things are involved. Okay, so plan is involved, construction requirement is involved, the structural requirement we have to consider. Designers, again, it's not only the structural purpose, but aesthetic should also be there. In different countries, people look for aesthetics, different kind of a shape, a creative shape, an innovative shape. So, and based on the slab system, lateral load resisting system, foundation, so all these things are considered in order to select the proper structural system. Okay, so here we have for the non-pre-stressed concrete slab bridges, the span. So based on the span also, you select what type of a bridge you require. So there is 5 to 14 meters, then there is 15, 12 to 20 meters. See, you can span to depth ratios, that also is considered. For continuous, it is 20 to 24. Solid slabs, 5 to 14 meters if it's in a highway. If it's a railway, 4 to 8 meters, solid slab is enough. So these kind of structural things are required for selection. So we have concrete solid slabs again, 14 plus a 9 to, if the span highway, if it is in highway, 9 to 24 meters, you select this one. Based on the span to depth ratio, 14 plus, then it should be simple. So in that way, you decide, there is a code for that, you decide that, whether you want a box girder. So again, when you want to use a box girder, span range should be 24 to 60 meter. Then there is a 15 to 30 meter span range. And we have the pre-stressed concrete slab bridges. Yeah, again, the span. You can see the highway and the railway up to 6 meter, up to 24 meter. So these all are there in the code. There is no restriction to memorize them. So you have to look for the code and then decide. So these and all, thus we have the bridge code, IRC codes for that, and other codes based on the country. So you have to go and search in that. There is a table available. You have to select based on that table. Again, precast, these are some of the examples which I am giving from the code. Okay, so 6 to 9 meters if it is a highway. It's a railway, 4 to 6 meters, solid slabs can be used. And the span to depth ratios should be 20, here 25 to 33. Similarly, one more for pre-stressed concrete girder bridges, you have a span range. So you should select based on the span range. Well, how do you want it to select the bridges, slabs, deck slabs, etc. So aesthetics, I told you, is very, very important. Okay? So engineers should not be limited to design calculations or monitoring. You can see that bad-looking bridges, if you see it is not attracting, it can create public discontent and despair. So it's always have a deep sensitivity to beauty. People have. So engineers must have a sense and feeling for the value and a sense of beauty. So highly subjective, non-dimensional, and generally non-quantitative bridges, they spoil the reputation of a civil engineering profession. They have an effect. So should not be an afterthought. These are some terms, tips. Keep it simple. Harmonial balance should be there for selecting. These are the selection processes. Surface details should be considered. Strength. So construction, based on the construction technology we saw, that the classification of the bridges, a lot of bridges again are there. Using precast, some of the construction technology we will see. The precast beam project, these are some of the projects available which were constructed. So how they were transported, how their construction was done. So this is a precast beam project. There's the full span precast project. See how the girders are brought here by cranes. They're called gantry girders. They have first the columns are built. Over that, you can see the shape now, the box sections, and they are placed. This is called full span. It sits over the full span. Sometimes half by half, half by half. So there's a very less span, and they will bring each girder and place it, not for the full span. Here you can see that's a full span. This full beam will sit over this pier. That's called full span cast project. Okay. So this is again one more full span cast project. So Taiwan, Singapore. And again, segmental construction means piece by piece. One piece, second piece. So they'll have that type of a construction. Here you see piece by piece they are putting and segmenting. You see the small piece here. The small piece will be brought and then attached like that. Attached, go on attaching. Next step they'll follow, go on attaching. You see a small piece here. So these kind of Sometimes they are lifted. The lifting process is very, very difficult. See, a lot of cranes will lift and place it. And that's how the small pieces are jointed together. Lifting frames. So here there's a stitching beam is there that will stitch. So how technology is very, very complex. And here you can see that again piece by piece they are bringing that, and they will try to attach it here. Again, one more piece, different shape. You can see hexagonal shape, and they brought and then placed over it by cranes. Here again they are drawing piece by piece, segment by segment. Okay. So the cranes will lift it and then place it. This is span by span truss work, steel. How they are erecting truss by truss, span by span, and there's a truss. They are erecting. These are called the I sections. So this is a picture of the Hong Kong bridge. So lots of bridges are available. You can just go through this. There's a penny base. All these are truss bridges. Then there's a span by span with launching gantry girders are there. So span by span, they will try to attach and then they will fix it. So this is one more construction method. Incremental launching. One crane, gantry girder will be there, will start, fix, and then it will try to increment. Then they will try to push it, and then one more span will be placed. That's called incremental launching. See here, the crane is there, they will cast it, and then this will move, they will cast it, this will move, they'll cast it. In that way, it will try to increment. This is a launching project. Increment by increment, they started creating. So you could have seen when you go through, see, the crane is brought and they will start fixing. This is an incremental, again, incremental launching project. So again, there are lots and lots of construction methods available. These are some of the construction methods based on the usage and construction methods. Bridges will be named. That's 48 meters of span length, 15 cantilevers were built. Your 71.5 meters of span length, 28 cantilevers. So some of the failure mechanisms of bridge, why they fail? It is due to the loss in load carrying capacity of the component or a member within a structure. They start failing. Okay? So failure is initiated when the material is stressed to the strength limit, and then it causes excessive deformations, which ultimately leads to the loss of life. That should be avoided. Total collapse should be avoided. So some of the, you can see that bridges have collapsed. It is very, very pathetic to see these kind of conditions. Sudden collapse due to some catastrophic conditions, which are very difficult. So what happened was, then only the tools had come into the picture. Different types of analysis tools had come, so that thanks to the technology where people were started using different analysis to find the failures, study the failures, and then they started using based on the failures, and then they started constructing. But even after that, some kind of bridges fail because of proper maintenance. So that cannot be avoided. Okay? So failure due to ductility in columns. This you can see the bridges, because of the column was not ductile, the bridge collapsed. This is due to the earthquake. Okay, now we talk about the loads, different types of loads available for the bridges. So we have normal dead load, live load, then there is an impact load, then we have the wind load, horizontal forces, longitudinal forces, centrifugal forces, buoyancy effect, current, effect of water current, thermal effects, then deformation and horizontal effects. So seismic loads. So all these loads have to be considered for the calculation of loads for the bridges, and these combinations are very, very important. The dead load is nothing but the self weight of the bridge elements. So different types, different elements of the bridge are deck, bearing coat, and stiffeners are there, parapet is there. So you have to take all these loads. A dead load, automatically if you use a tool, if you may do it manually, then all loads should be considered dead loads. Okay, then we have the light loads. We all know that vehicles will be moving along the bridge, so we have to consider the vehicle loads also to give a safe bridge. We will see all these. Then when you talk about the vehicle loadings, there are different types of loadings. Class A, again there's a code, Class A, Class B. So Class A, very, you see, like highways, cities, heavy loadings. There is dragged type, wheeled type of vehicles are there. So we have to consider all these things. We have an A loading. This is taken from the code. So if the vehicle is 7.2 meters, what is the load available on each tire? That is each wheel. You can see the 12-meter width and 0.3 meter, 7 meter. Each, this is the wheel on the loads, on the wheel loads. So then we have the loading Class A. Class B loading, timber bridge. Here we have a standard bridges, permanent bridges. Here we have timber bridge, like temporary bridge for military purposes. This is a loading which IRC Class A and Class B loadings. We'll be using this part tomorrow. Here we have, you can see, understand this first. So when you talk about the vehicle loads, each load, each wheel will have a load to carry, and the space between this distance of two wheels has to be considered. So here it is saying 1.1 meter. From the front to back, it is 3.2 meter, and this is 1.2 meter. Okay, then there is a gap, 4.3 meter, and then this. So this is type of an axle load. What does that axle load means in kilonewton? 68 kilonewton. Width will be 500 mm. Width is on the plan. See here it is 1.8 meter. Two wheels will be there, no, in a vehicle axle. So this is the one wheel which we are seeing here. The other wheel is there, and it is 1.8 meter width. So that wheel has to move along the bridge. We will use this load and apply it on the bridge, and we will see how the wheel is going to have an effect on the bridge wheels. Then we have the impact loads. So this impact load on the bridge is due to sudden loads when the vehicle is moving on the bridge. This is an impact load. Then we have the impact load factor you have to consider. 25% up to 9 meter. All these things will be available in the code, and we have to use that. Okay. Then these are some of the impact factors for the wheel load, which we saw just before. So this is some criteria which you have to take. The impact factor should be given. They are given it in the form of a graph, so that you can consider this also. So when the span is this much in meters, so if it is RCC steel, you have to take impact factor, which is the formula IF is equal to A/B plus L. B are constant, C and B are constant. Apart from the superstructure, impact factor is considered for the substructures also. Okay, so these are the impact factors up to depth of 3 meters. How do you take the impact factor? Then there is the wind load. So wind loads have to be considered on the bridges. So wind load should be considered for the substructure also. For long span, wind is considered in the design of the superstructure. Then these are the longitudinal forces on the bridge which are caused by the braking and accelerating on the vehicle. When the vehicle stops suddenly, what happens? It induces longitudinal force on the bridge. So that also IRC recommends 20% of the light work should be considered. Then if the bridge is built on horizontal curves, then the centrifugal force is called super elevation forces or centrifugal force have to be considered. Okay, while turning and all. So that is calculated by a formula. Okay, how the load is calculated is shown in kiloton per meter. These are the factors that you have to consider. Buoyancy effect. Submerged, when you want to build a submerged substructures on the water, so you have to consider deep water bodies, all these things. Sometimes it's negligible, but you have to consider. Then water current. If you are going to build the bridge on water, then water current forces should be considered. So water forces by water currents are maximum at the top and the zero at the water level or on the bed level. There's always a trapezoidal distribution. So that is the formula that you have to use. These are the thermal stresses. Okay, due to temperature. That also should be considered. Some effect is there. To resist this, expansion joints are also provided. Then have the seismic loads. So seismic loads, you know, the earthquake loads are available. Now the code has been split into different categories based on the bridges, based on buildings. So that forces also you should consider for calculating the strength of the bridge, whether the bridge has to be built in the seismic or the earthquake zone. That is very, very important. Then deformation and horizontal effects. So they may be change in shrinkage in concrete. These are called the deformation stresses occurring due to this material. Then we have the erection stresses. Okay. So now these kind of stresses and the loads and the type of bridges that you saw. So tomorrow we will be continuing with this so that we will take an example of the bridge and we'll try to model and apply the vehicle loads and see what is how the displacements are occurring and how the deflection is being studied, and we will analyze that. So I stop with this here. So any questions, any queries that can be answered? Okay, Abhishek. Thank you, Abhishek. I think you don't have Akhil ready. You don't have anything? Any doubts? Okay, Akhil. Harshil, okay. Okay, Abhishek. We have, I think STAT is more better because if this is a question given by Hashim, I think STAT is more better. So we'll take STAT. How do we anchor? This is by more about erection stresses. Later, I'll explain. Okay, thank you, Ruchi. Guhan, thank you. Yes, Monica, thank you. Karthik, thank you. Yeah, thank you all. Any doubts you can post? Okay. How do you anchor cables at the end of the bridge? Now they have some jack which is available. The jack, they will pull it and anchor it. with the help of a jack, and they will. There's a bolts, big bolts are available. They will fix it, tighten it.
Okay, so thank you so much everyone for joining this wonderful session. We'll be conducting tomorrow class on the concept of bridge analysis using a StatPro software. So like tomorrow we'll be starting at the same time 6:30 p.m. and we'll be providing you today's study materials on your WhatsApp group. You may connect it over there. We'll be sharing the attendance sheet also. You can fill your attendance. So thank you so much, ma'am.
Yeah, thank you.
So we'll be ending today's session here. So we'll meet tomorrow at 6:30 p.m. You can fix as a reminder. We'll send you the tomorrow link tomorrow evening. Thank you so much.